Okay, hello everyone. Let us continue the second part of today's class. Okay, let us go to the handout. Let us see the new announcement. Okay, so the new announcement is the handout of chapter 2 has been updated, version 2022-0429. Hello everyone, I have uploaded the latest version of the handout of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, handouts, chapter 2 handout 2022-0429.pdf. Best regards, Wei Zhen. Okay, next let us continue the first part of today's class. Okay, in the first part of today's class, we have explained what is convex open set. Okay, why do we need to know what is a convex open set? Because it is in the solution of the subgradient. And the subgradient is in the problem of what is subdifferentiable. And subdifferentiable is in the problem solution to problem 2. What is stochastic gradient descent? Okay, so let us continue. Okay, let us see problem 4. What is a subgradient? Okay, let us see. Okay, solution: if f is a function from U to R, is a real-valued convex function defined on a convex open set in the Euclidean space R to the power of n. Okay, what does this mean? R to the power of n. Okay, it means that it's an n-dimensional Euclidean space. Okay, or an n-dimensional real vector space. Okay, a vector v in that space is called a subgradient at a point x0 in U if for any x in U one has f of x minus f of x0 is greater than or equal to v dot x minus x0. Okay, where the dot denotes the dot product. Okay, the set of all subgradients at x0 is called the subdifferential at x0 and is denoted partial f of x0. The subdifferential is always a non-empty convex compact set. Okay. We will explain what is a compact set later. Okay, these concepts generalize further to convex functions. F is a function which is from U to R. Okay, on a convex set in a locally convex space V. Okay, we will explain what is a locally convex space later. Okay, a functional V star in the dual space V star. Okay, we will introduce what is a dual space later. It's called subgradient at x0 in U if for all x in U f of x minus f of x0 is greater than or equal to v star times x minus x0. Okay. The set of all subgradients at x0 is called the subdifferential at x0 and is again denoted partial f of x0. Okay, it is the same as the previous sentences after equation 22. Okay, the subdifferential is always a convex closed set. Okay, what is a closed set? Okay, we will explain it later. It can be an empty set. Consider, for example, an unbounded operator. Okay, we will explain what is an unbounded operator later, which is convex but has no subgradient. If f is continuous, the subdifferential is non-empty. Okay, let us go to problem 5. Okay, we have teach it and the solution. And problem 6. Okay, what is a convex set? We have talked about it. Okay, and problem 7. Okay, we have talked about it. Okay, then problem 8. What is an open set? Okay, we have introduced it. Okay, so next let us go to problem 9. Okay, problem 9. Okay, so problem 9, what is a closed set? Okay, solution in geometry, topology, and related branches of mathematics. A closed set is a set whose complement is an open set. Okay, then problem 10, what is an open ball? Okay, we have explained what is open ball. Is an open ball. Excuse me. And the first appearance of the open ball is here. Okay, so next. Okay, problem 11. What is a compact set? Okay. Solution. Various definitions of compactness may apply depending on the level of generality. A subset of Euclidean space, in particular, is called compact if it is closed and bounded. Okay, because the Euclidean space is the space in our real world. Okay, for example, in our real world, it is an Euclidean space R to the power of 3. That is 3-dimensional real vector space. Okay, then what is bounded mean? Okay, problem 12. What is a bounded set? Okay, solution. In mathematical analysis and related areas of mathematics, a set is called bounded if it is, in a certain sense, of finite size. Okay. Conversely, a set which is not bounded is called unbounded. Okay, please see figure 18. Okay, let us go to figure 18. Okay, figure 18 is an artist's impression of a bounded set top. Okay, we can see that top, it is a bounded set because the size of this set. Okay, what does the size of this set mean? Okay, in the two-dimensional plane, it means the area of this triangle. Okay, and of an unbounded set button. Okay, this is an unbounded set. Okay, because the area of this set or of this angle inside the angle is infinite. The set at the bottom continues forever towards the right, so it can be extended to the right to infinity. Okay, let us go back to figure the first time we mentioned figure 18. Okay, so we have explained what is a bounded set in problem 12. Then let us go to problem 13. We still need to define a bounded set in the real numbers. Okay, please see figure 19. Let us see figure 19. It is a real set with upper bounds and is suprema. Okay. In figure 19, here is a set M, which consists of red points here, 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 and here. Okay, this is the set M. Okay, and the set M has many upper bounds. Okay, for example, this is the upper bound of set M, and this and this and this are upper bounds of set N. However, there is only one supremum. Okay, what is the meaning of supremum? The supremum is the least upper bound. Okay, that is, among all the upper bounds, we choose the smallest one. Okay, or the minimal one. Okay, it is the green point. Okay, so a set S of real number is called bounded from above if there exists some real number k. Okay, not necessarily in S, such that k is greater than or equal to S for all small s in capital S. Okay. The number k is called an upper bound of capital S. Okay, we can see that the green one and the brown, the three brown points are all upper bounds of the set N. And we can see that these 3 points are not in the set M. Okay, however, they are all greater than or equal to all of the blue points. Okay, on the in terms of the value on the real number line. Okay, the terms bounded from below and the lower bound are similarly defined. Okay, a set S is bounded if it has both upper and lower bounds. Therefore, a set of real numbers is bounded if it is contained in a finite interval. Okay, so next, problem 13. What is a locally convex space? Okay, solution. Suppose X is a vector space over K, where K is a subfield. Okay, we will explain what is a subfield later. Of the complex numbers, normally C itself or R. Okay, R is the C is the set which contains all complex numbers, and R is the set which contains all real numbers. A locally convex space is defined neither in terms of convex sets or equivalently in terms of semi-norms. Okay, let us see first the definition via convex sets. Excuse me. Okay, a subset C in X is called first convex if for all xy in C and 0 is smaller than or equal to t and t is smaller than or equal to 1. Okay, sorry, I need to go to the toilet. Please wait me for 1 or 2 seconds. Sorry, 1 or 2 minutes. Thank you. Okay, I am back. So let us continue. A subset C in X is called first convex if for all xy in C and 0 is smaller than or equal to t. Excuse me. Excuse me. And t is smaller than or equal to 1. Then t times x plus 1 minus t times y is in C. Okay. In other words, C contains all line segments between points in C. Okay. Okay. Do you remember we have seen a figure for a convex set example? Okay. Let us go back to the figure. Okay, this is a convex set. Okay, because you can arbitrarily choose 2 points. Okay, different points x and y in the set, and you use a line segment to connect between points x and y, and the line segment will also be in the set. Okay, so this is a convex set. Okay, next let us go back to the convex. Okay, here. Okay. Okay, 2 circled. If for all x in C, okay, and the scalars s, if the absolute value of s is equal to 1, then Sx is in C. Okay. If k is equal to R, that is, the set contains all real numbers. This means that C is equal to its reflection through the origin. Okay, what does it mean? Okay, let me draw a figure for you. Okay, let me open the Microsoft Word. Okay, and open a blank document. Okay, so now let me draw. So if we have real numbers, this is the line of the real numbers, and this is the origin, 原点, and here is the x, so and a scalar s, and we know that the absolute value of s is equal to 1, is equal to 1. So we know that s is equal to positive or negative 1. It is easy. Then Sx is in C. So it means that we see that Xx is in C. It means it implies that S and minus X is in C. Here. So this means that C is equal to its reflection through the origin. For example, X is here, and there is another is a reflection of X, which is minus X. Through the origin. For K be equal to C, where C is the set of all complex number. It means that for any X in C, C contains the circle through X centered on the origin in the one-dimensional complex subspace generated by X. What does this mean? Let us clear. Clear the. Clear this. Clear this. Writing. Clear. 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 Let me draw a graph for you. So here this is the complex number plane. So this is the origin. And here is the real part. And this is the imaginary part. Like this. That if for any X is in C, let us draw a point. For example, this point, this is X. X is in C. C is a subset in X. So and now if S, the absolute value of S is equal to 1. So let me write this. The absolute value of S is equal to 1. But now it is the complex number plane. So we know that S can be written as S is equal to e to the power of j theta. Like this. And theta is in the interval 0 to 2 pi. Like this. And then Sx is in C. So we can know that if S times X, it is equal to ej theta Okay, X. Okay, it is also in C. Okay, okay, it is 25 minutes. Let us take a break.